Here we're going to look at question 84 from the NSAA 2018 paper. In this question, we're told to have a collision between two spheres, x and y. We're also told that their respective masses are m and 2m, and that they are initially travelling with speeds of v and 2v respectively, straight towards each other. The two masses collide head-on, and then we're given a velocity time graph for our sphere x. The question asks us to find the velocity time graph for y. So if you would like to have a go at this question, then now's the time to pause, otherwise let's have a go at it. Now, whenever I'm given a collision question, what I like to do is draw a diagram. I think it's quite helpful because it lets you visualise exactly what's going on, and it's a nice concise way of keeping all of our variables up on the page. So let's go ahead and do this. So in our collision before the collision, we have our mass m moving at a velocity v to the right, and our ball of mass 2m moving at a velocity 2v to the left. Then, after the collision, our mass m is travelling with the same velocity v, but just in the opposite direction, and our mass 2m is travelling with an unknown velocity u. So I've labelled this as being in this direction, just because that's probably what you would expect. But if it's going to be in the other direction, then our u value will just turn out to be negative. So how should we try and solve this problem? Well, as we always do with collisions, the best thing to use is probably conservation of momentum. Now, we could try and use conservation of energy, but energy isn't always conserved in collisions, depending on if they're elastic, inelastic. We have no idea. And with our equations of energy, it's not always obvious where energy is being lost as well. Whereas with momentum, it's always going to be conserved. So it's a much safer bet. Bearing that in mind, let's set up our equation for conservation of momentum. So our initial momentum here on the left is going to be equal to our momentum afterwards written here on the right. So the initial momentum is just the momentum of our mass m, which is just going to be mv, plus the momentum of our mass of 2m. So it's 2m multiplied by this velocity, which is negative because it's in the opposite direction. And then our momentum afterwards, is going to be m multiplied by minus v, since this v is in the opposite direction to what it was initially. And then the momentum of our mass of 2m is just going to be 2mu, where u here is positive because I labelled it as being in this direction. We can go ahead and simplify this a little bit, and our left-hand side becomes minus 3mv, which is going to be equal to our right-hand side of minus mv plus 2mu. Then bring our minus mv over onto the left-hand side by adding. Then we get that minus 2mv is equal to 2mu, and therefore u is going to be equal to minus v. So the final velocity of our mass 2m is going to be v to the left in this direction. So both of our projectiles are going to actually move together at the same velocity v in the same direction. Now, bearing in mind this information which we found out, we can go ahead and try and plot our graph for the velocity time graph for our particle y. Since the initial velocity is going to be minus 2v, and then the final velocity is going to be minus v, then our velocity time graph should look like this. This graph is then going to correspond to answer F given in our question.